Section 8.3 is actually a reversal of Section 8.2. In Section 8.2, if we knew something was a parallelogram, then we knew certain properties about that quadrilateral. Now, in Section 8.3, we're going to prove that quadrilaterals are parallelograms given those properties. So it's just going to be the opposite. So we're going to be proving things are parallelograms rather than starting with something's a parallelogram and then knowing things about it. So here's our first two theorems. Theorem 8.7. If both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. So again, before we would have written it as if a quadrilateral is a parallelogram, then we know the opposite sides are congruent. But now we're saying if both pairs of opposite sides are congruent, then we know it's a parallelogram. So it's the opposite of it. Theorem 8.8, if both pairs of opposite angles of a quadrilateral are congruent, then the quadrilateral is a parallelogram. Again, in the last section we started with if a quadrilateral is a parallelogram, then we knew the opposite angles were congruent. Now we're saying if we know that both pairs of opposite angles of a quadrilateral are congruent, then we know it's a parallelogram. So again, we're proving that quadrilaterals are parallelograms in this section. Now let's look at example number 1. It says the figure shows a part of a stair railing. Explain how you know that support bars MP, which is right here, and NQ, right here, are parallel. So if we can prove that this quadrilateral MNQP is a parallelogram, then I would know that opposite sides are parallel by the definition of a parallelogram. So let's prove that this quadrilateral is a parallelogram. So I would start this by saying that MN is congruent to PQ, since as you can see here, they have the same measure. I also know that MP is congruent to NQ, since again, they have the same measure. They're both 3 feet. So now we see that both pairs of opposite sides are congruent. We can conclude that quadrilateral MNQP is a parallelogram according to our first theorem, Theorem 8.7 from the previous slide. It stated that if both pairs of opposite sides of a quadrilateral are congruent, like we have here, we knew that MN and PQ were congruent and MP and NQ were congruent, then the quadrilateral is a parallelogram. So now that we've proven that MNQP is a parallelogram, by definition, opposite sides are parallel. So therefore, we know that MP is parallel to NQ, which is what we were asked to show. We were asked to explain how we know that the support bars MP and NQ are parallel. So again, first we proved that the quadrilateral was a parallelogram since opposite sides were congruent. And then by the definition of what a parallelogram is, because remember the basic definition of a parallelogram is that opposite sides are parallel, we know that MP and NQ are parallel. So now we have example number 2 in quadrilateral WXYZ. So first notice that it's not telling us that it's a parallelogram, it's just a quadrilateral. We see that the measure of angle W is 42 degrees, the measure of angle X is 138 degrees, and the measure of angle Y is 42 degrees. So the first thing they want us to do is find the measure of angle Z, and then we're asked, is WXYZ a parallelogram? So of course, let's make a picture to start answering our questions were asked. So here's WXYZ. Make sure you label them in the order that you're given. So remember, once you start, you just go in a circle. So WXYZ, we're told that W is 42 degrees, X is 138 degrees, and Y is 42 degrees. Since it's a quadrilateral, we know that the sum of the interior angles of a quadrilateral is 360 degrees. So if we wanted to find the measure of angle Z, like we're asked, we would take the total, 360, minus the 42 of angle W, minus the 138 of angle X, minus 42, which was angle Y, and we'd end up with the measure of angle Z is 138 degrees. Then it asks us then, is WXYZ a parallelogram? So notice that opposite angles are congruent. By theorem 8.8 from the first slide, if we know if both pairs of opposite angles of a quadrilateral are congruent, then the quadrilateral is a parallelogram. So we would say, yes, WXYZ is a parallelogram because opposite angles are congruent, which by theorem 8.8, if we know that both pairs of opposite angles of a quadrilateral are congruent, then the quadrilateral is a parallelogram. And now we have two more theorems. Let's start with theorem 8.9. If one pair of opposite sides of a quadrilateral are congruent and parallel, then the quadrilateral is a parallelogram. So looking at the diagram, if we see that just one pair, so BC and AD, they're not just congruent, but they're also parallel, then we can conclude that quadrilateral ABCD is a parallelogram. So again, just one pair of opposite sides are congruent and parallel, then we know that the quadrilateral is a parallelogram. And theorem 8.10, if the diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. So again, if you know that the diagonals bisect each other, so they're meeting at each other's midpoint, then you would know that the quadrilateral is a parallelogram. So in the following examples, we'll put these two theorems to work. Example number 3 says, state the theorem you can use to show that the quadrilateral is a parallelogram. So for part A, we see that we have two pairs of sides that are congruent and parallel. So that would be the theorem that states that if one pair of opposite sides of a quadrilateral are congruent and parallel, then the quadrilateral is a parallelogram, which was theorem 8.9. For part B, we see that we have two pairs of opposite sides that are congruent. The theorem that states if both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram, which was theorem 8.7, the theorem that we started this section with. And then finally, part C, notice that we have two pairs of opposite angles that are congruent. That would go with the theorem that states if both pairs of opposite angles of a quadrilateral are congruent, then the quadrilateral is a parallelogram, which was our second theorem from this section, which was theorem 8.8. Example number 4. For what value of x is quadrilateral RSTU a parallelogram? So at this point, it's just telling us that the quadrilateral is only a quadrilateral, and it wants to know what would x have to equal for the quadrilateral to become a parallelogram. So notice that we are shown the diagonals. So I'm going to think back to theorem 8.10 that states, if the diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. So notice that diagonal SU is being bisected, but we are not told that diagonal RT is bisected. But we could make it so that RT is being bisected if we set the 8x minus 32 equal to the 4x. So then we just need to figure out what x would be equal to in this case to make the two parts of the diagonal equal to each other, meaning that they're being bisected. So it's just as a matter of solving for x. So we're going to subtract 8x from both sides. So I'd have negative 32 equals negative 4x. Divide both sides by negative 4, and I would end up with x equals 8. So if x equals 8, that would make this segment equal to this segment, which in turn would make both diagonals bisected. So according to theorem 8.10 then, RSTU would be a parallelogram. And finally, we end this section with a concept summary. These are the 5 ways to prove that a quadrilateral is a parallelogram. So this is just referring to all of the theorems and the definitions that we've talked about so far. So to start with, the definition of what makes something a parallelogram. If both pairs of opposite sides are parallel, then you know that the quadrilateral is a parallelogram. Next, if you're able to show that both pairs of opposite sides are congruent, then the quadrilateral is a parallelogram. That was theorem 8.7. Number 3, show that both pairs of opposite angles are congruent. So opposite angles are congruent. That means that the quadrilateral is a parallelogram, which was theorem 8.8. Number 4, show one pair of opposite sides are congruent and parallel. So not only do they have to be congruent, but they also have to be parallel, but we only need one pair of opposite sides. And that would be theorem 8.9. And finally, The fifth way is to show that the diagonals are being bisected. So if I can show that both diagonals are bisected, then I can prove that the quadrilateral is a parallelogram. This would be a great thing to have in your notes to refer to when you are trying to decide if something's a parallelogram or not. That's it for this section. Make sure you jot down anything you did understand that we can cover before we move on, and we'll see you then.